As I mentioned before, the spatial two-stage least squares estimation of the spatial lag model is nothing but a special case of two-stage least squares with particular instruments. And to see some of the implication of this for our estimation, we'll consider some of the regularity conditions that underlie two-stage least squares estimation. So these regularity conditions are a set of assumptions that guarantee that the two-stage least squares estimator is consistent and also is asymptotically normal with a given variance matrix. Now, as I mentioned in the discussion of maximum likelihood, the asymptotics in the spatial case are not a straightforward application of the standard non-spatial case, but they require special central limit theorems that take into account the particular type of dependence created at the boundary of the data set as it expands towards infinity. We discussed this under the maximum likelihood estimation and saw that the key concept there is that of a triangular array. Now, we don't have time to get into technicalities about this triangular array. The only main thing to remember is that these properties of consistency and asymptotic normality are not obtained using the standard results, but they need specialized results, and these are highly mathematical. Let's look closely at two specific regularity conditions, two specific assumptions in the two-stage least squares framework. The first one is that the probability limit, the PLIM, of the average of the cross product of the instrument matrices, Q prime Q, is a finite non-singular matrix. So in other words, this requires that the columns of the instrumental variables matrix Q are independent, are linearly independent. So in our particular case, where the instruments will be spatially lagged variables, spatially lagged explanatory variables, the Wx, this requires that Wx and x are not linearly dependent, because if they were, then this product of the matrix Q prime Q would not be non-singular, it would be singular. So what this means in practice is that Wx cannot include a constant term, because for row standardized weights, the spatial lag of the constant and the constant are exactly the same. So in the Wx, we'll have one less column than x, the column that corresponds to the constant term. This also will have implications later in terms of interpretation. Now, there are other situations where Wx can be equal or nearly equal to the original variable x when we have dummy variables, especially dummy variables that might correspond to regimes, where again, depending on the spatial weights, there are situations possible. For example, if the weights are limited to the regimes themselves, then any dummy variable for the regimes will be equal to its spatial lag, and that would have to be eliminated as well. So this is a tricky case that sometimes sneaks up on you. The key to remember is this very fundamental requirement that the matrix Q prime Q on average, 1 over n, has to be non-singular, which excludes columns in Q that are the same and that might create a linear dependence in the matrix. The second regularity condition that requires some of our attention is this fundamental notion that the probability limit, the PLIM, of the average of the cross product of the instruments with the original variables, where the z include the endogenous variables, is again a finite and full column matrix. So again, this excludes linear dependencies and cases where this product does not maintain the full column rank. In other words, at least one other exogenous variable is required other than a constant, because the instruments do not include the spatial lag of the constant term. So if there isn't any other x, then we don't have instruments. So in other words, this does not work for a pure, so to speak, spatial autoregressive regression where there is no there are no exogenous variables. So the specification of y equal rho wy plus error term, which is a pure spatial autoregression, cannot be estimated by means of spatial two-stage least squares. And there's another wrinkle to this, which is a little bit more technical, is that because the instruments have to exist and have to be correlated with the original variables, we cannot have a situation where all the variables, the regression variables, are zero. In other words, the standard null hypothesis for an F-test or an F-type test is invalid. And so this has some technical implications for how the tests can be carried out. And basically, it means that, again, spatial two-stage least squares cannot be used to estimate a pure spatial autoregression. Okay, how does it work then? It's a very standard situation. We construct a matrix Q of instruments, the instrumental variables, the original exogenous variables, their spatial lag, maybe the second order spatial lag, and maybe higher order if warranted. And then Q is just like any other instrumental variables as a matrix used in two-stage least squares. And the estimator has the exact same expression as the standard textbook case, this very complicated matrix expression, Z prime Q, Q prime Q inverse, Q prime Z, all inverted, and then Z prime Q, Q prime Q inverse, Q prime Y. That's the estimator, and its variance in the case of homoscedasticity is sigma squared Z prime Q, Q prime Q inverse, Q prime Z, the whole thing inverted. The spatial two-stage least squares estimation is consistent, but it is not the most efficient because it doesn't use all the information about the conditional expectation of the spatial lag. Remember, we made a simplification in that after we wrote out the full expression, we said, well, we'll just pick the spatial lags of the explanatory variables as the instruments, but that doesn't take into account all the information that we have in that conditional expectation expression. So that's a reason why it's good enough, it's consistent, but it's not the most efficient. Now, in very large data sets, this is not going to matter very much, but it does matter in smaller data sets. So just as spatial two-stage least squares is just an application of standard two-stage least squares with specific choice of instruments, we can also introduce heteroscedasticity. And we do this by using the standard White correction for the presence of heteroscedasticity of unknown form. The estimator is the same, nothing changes there, but we get new sets of standard errors which are robust to heteroscedasticity. So if we suspect heteroscedasticity, which is pretty standard in a cross-sectional equation, we should really use the White correction for heteroscedasticity of unknown form as the estimate for the standard errors and as the basis for statistical inference. So the coefficients don't change, but the t-tests will be affected because they're different standard errors. So in a nutshell, spatial two-stage least squares, there's nothing to it. This is just a standard application of two-stage least squares. However, to get the properties of consistency and asymptotic normality, we have to use a different mathematical framework of triangular arrays, and we have to be careful with the choice of the instruments. Some of the spatial lags may be inadmissible, specifically the one for the constant term, but also in some cases with dummy variables, we may run into problems with those instruments. And then finally, because of one of the other regularity conditions, the correlatedness of the instruments with the original variables, we cannot use the spatial two-stage least squares in a pure spatial autoregressive specification.